This is Precalc Chapter 3.3, Day 2. We're going to start off talking about Descartes' Rule of Signs. But before we talk about that, we need to talk about the fact that, sure, we made a list of potential candidates for rational zeros, and sometimes these lists only had 3 or 4 options. Then all of a sudden, bless you, then we started realizing that if that number at the end, that constant, was something like a 36 or a 64, and it was over, and then the first leading coefficient is like a 12, you could potentially have 30 to 40 different options to have to check, right? Because the factors are 36 over the factors of 12, there's a lot of them. And so what we can come up with is there's ways to start to eliminate some of those. And one of those ways is to look at variation in sign. So we're going to talk about the variation in sign real quick. The variation in sign, guys, is when adjacent coefficients have opposite signs. That means their signs changing. Now this has to be in standard form. We don't care about placeholders because placeholders won't have the effect on anything. But as you can see, P of x here is in standard form, highest to lowest power. All we're doing is we are going through and we are going to say, where are the signs changing from a positive to a negative to a negative to a positive? And so you can see that it starts off positive and then changes to negative. Stays negative, goes back positive. Stays positive, goes back negative. There are 3 variations of signs. Those 3 changes actually mean something. And so Descartes comes up with this idea, or finds this rule that works. And it's really kind of cool. It says, let P be any polynomial with real coefficients. You're not going to have imaginary numbers as your coefficients. First of all, that wouldn't be a polynomial. So, first thing, you can determine the number of possible positive real zeros is either equal to the number of variations in sign or is less than that by an even whole number. So you have to subtract 2, subtract a 4, or subtract a 6. So let's go back to our example. In our example, P of x itself had how many sign variations? 3. So this problem could potentially have 3 positive answers. 3 positive answers, or 1 positive answer, or 1 positive solution, we say. The rule says that the number of changes in variation is equal to the number of positive solutions, or less than that by even numbers. So there's either 3 or there's 1. You can't be negative 1. So it's 3 or 1 possible positive solutions. And the cool thing is, guys, this works for the negatives as well. But for the negatives, you need to change it a little bit. And you need to change it by plugging in a negative x and evaluating. So to do that, you need to do P of negative x. This one takes a little bit of finesse, right? Takes a little bit of thinking. Minus 3 times negative x to the 5th. Minus, negative x to the 4th. And you have to remember your order of operations, otherwise you'll end up not doing too well on this one. Very easy to mess up on your signs. Now, is any of this even needed? No. But if you have something like the example here of to the 7th power, bless you, you're going to have 7 possible real solutions. You're going to want to find them all. So if all of a sudden you realize in this problem that you found 3 positive real solutions, are you going to be hunting for another positive real? No. It's kind of a cool thing. So if I start to evaluate, an odd power on a negative will keep it negative. So I think everybody should realize that this will be a negative 5x to the 7th. Yes? The negative on inside here to the 5th power gets to go to the outside, which cancels with the 1 there. So it's a positive 3x to the 5th. What happens with the 4th power, though? Anything to the 4th power turns to be positive at all times. So the negative on the outside gets to stay, does not be affected, or is not affected. Same thing with the 2x squared. Adding a negative x is the same thing as subtracting x minus 3. And then we just take a look at the sign variation again. Starts negative to positive, that's 1. Positive to negative is 2. Negative to positive, 3. Back to negative. And stays negative, right? How many sign changes? So there are 4 negatives, or what? Less than that by an even whole number. 2 negatives, or 0 negatives. Now, this potentially could be true because the degree is 7. If I had 3 positives and 4 negatives, I would have how many solutions? 7. Notice, I'm not asking you to find them. Watch your directions in your homework, because some of them are just to state how many potential positive or negative answers or solutions, okay? Do you think you guys can try one of those on your own? Yep. Okay, I want you guys to just determine the possible number of positive and negative zeros of this polynomial. It's the 6th degree, already in standard form. I'll give you guys a couple seconds, or a minute. Okay, guys, how many sign variations are as it stands? So there's 1 right there, so there is 1 positive. Generally, finding the positive solutions, not the difficult part, because you just have to use the function that's given to you. It's to find the negative potential solutions. Now, we got to put p of negative x in. Can we do this potentially just thinking in our head? I'm going to take that and bring it to the 6th power, which makes it, or keeps it, positive. I'm going to raise it to a 5th power, which makes the negative go out and makes it a negative 4x to the 5th. Again, same principle happens, and so I get a negative 3. The negative would cancel, minus 3. Is that what you guys got? Okay. How many sign variations do we have now? 3. Here, here, here. So there's 3 negative or 1 negative. That's what you needed to list. Easy enough? Why is this important? It's important because if you already found a positive solution by guessing, I'm not going to keep guessing or checking more positive answers. It only makes sense. So that potentially could limit the amount of choices we have. Next one is what happens if we have an upper and lower bounds? What if I told you that, hey guys, there's something, as we're checking all of our answers over and over and over and over again, trying to find a solution, what happens if all of a sudden you recognize something as part of the quotient in the remainder, the answer part on the bottom? There's a pattern. If I choose to put for checking x minus b. So if I divide by x minus b, which means you're checking positive solutions, yes? And so if you check a positive solution using synthetic division, and the quotient remainder row, the very last row, has no negatives, means all positives, that means that the value of b is the biggest number that you should have to check. You don't have to check anything higher than that. So here's the cool thing. So if your list included numbers like 4, 10, 28, 36, right? And you checked 4, and 4 came with all positive answers on the bottom, or entries, 4 is the largest number that it could ever be. Don't even check the rest of them. Awesome. Likewise, guys, this one's a little bit different, is that if you are trying to divide out using synthetic division a negative choice, where a is less than 0, so this is a is less than 0, and if the row contains the quotient remainder entries that are alternately non-positive and non-negative, so they go positive, negative, or negative, positive, that means that you just found a lower bound. So what we're doing is we're taking the ends of the choices and bringing it closer together, making the list even smaller. How awesome would that be if you had known that yesterday, potentially, trying to find all 5 solutions? So, the first example we have here is I'm telling you that I got a polynomial that all of the answers lie between -3 and 2. The reason I'm telling you this time is that you can see that when you put -3 in using synthetic division, or 2, you can recognize the patterns that we're stating above. So, do I need placeholders on these? Okay, so 1, 0, -3, 2, -5. You guys can agree with this? Which one do you want to check? You want to check -3 or 2? You got to check them both anyways. -3. Bring the 1 down. -3 times 1. -3. Add it. It's -3. -3 makes a +9, which add those together gives you a... It's not going to work, but that's okay. It's okay. It's 6. 6 times -3 is -18, which is a -16, which is positive, bless you, 48, which is a 43. So this is not right. But wait a minute. Do you recognize the answer goes, we put a negative answer in. We tried it. 1, or positive, negative, positive, negative, positive. That means -3 is a lower bound. That's what it means. I should be able to check the exact same thing. With 2, but 2 should end up being a upper bound. 2, 4, 1, 2, 4, 8, 3. They're all positive. I went pretty quick there. I'm just trying to show you this idea that works. That means 2 is an upper bound. Why could that be potentially a powerful thing? Let me etch out a little spot here. Guys, if I wanted to make a list, would you guys say that's the factors of 5 over the factors of 1? This one maybe is not as good because you only have this list, right? What I'm trying to say is, would you even test 5 or -5? That's what I'm saying. Okay? So don't even test 5 at all, or negative 5. You would test 1 and negative 1. But remember though, here's the thing. You could use these things more than once. So 1 or negative 1 could potentially be used several times. It has a multiplicity, remember? We graph things like that. They have a power on them then. So it could be using two positive ones and 2 negative ones to create that. That's an option. Or there could be some imaginary solutions in this, or there could be irrational solutions. Clear? So, to test this out, I want you guys to factor this one completely. Using upper and lower bounds, Descartes' rules, quadratic formula potentially. I'll give you guys some time. Work together. It's okay. So as you guys are working, I'm going to go through the Descartes. Positive to negative to positive. So I'm going to say that there are 3 possible positives or 1 positive.
Wait, why would 2x plus 5x to 4 be a change?
Correction, there is no change here. So there's a positive to negative and then back to negative to positive. So 2 positive or 0 positive. If I put p of negative x in, I get negative x to the 5th, 5x to the 4th, plus 8x cubed, minus 14x squared, minus 6x plus 9. Let's check this. Negative to positive, positive to negative, negative to positive. So we're going to say 3 negative or 1 negative. Okay? So we potentially have all 5 answers, 2 of them positive, 3 of them negative. But there also could be some not so nice things in there as well. Let's start going here. Now, to make it so we can kind of show some things. Is it Gracie? Did you say you found an upper bound? No. Helen. Okay, what did you find? Or is it 9 halves? So 9 halves. So we go back to be 2, 5, negative 8, negative 14, 6, and 9. Bring the 2 down. 2 times 9 halves is 9. 9 plus 5 is 14. 14 divided by 2. 7 times 9. 63. Add a negative 8. What, 55? Now this one's going to be not so fun. I forgot to make my list. We'll make our list right after this. What's 4.5 times 55?
It's 2 47.5.
0.5?
Yeah.
And if I add a negative 14 to that, it's 237 or 230, oh, sorry, 33.5. Divide that by 2, multiply it by 9. I think at this point you're going to say it's not going to work, but we still can show that it's going to be all positives.
The 2 positives that work are work half.
Hey guys, what's this times 9 halves? So I paused it to get the last couple numbers here, but do you recognize that all of this quotient and divisor are positive? Which means 9 halves or 4.5 is upper bound. That means I'm not going to check anything after 4.5. Now, why is this important? The thing I forgot to do was make a list, guys. I forgot to say it's 9 over 2, which is 1, 3, 9 over 1 and 2. Which means plus 1, 3, 9, 1 half, 3 halves, and 9 halves. That only helped us eliminate, guys, 9. Because 4.5 is bigger than most of those numbers. But potentially there could have been more. Homework on page 287, 31 through 32, 53 through 54, 68 through 69. Have a great day.